discuss electrostatic and capacitance, lecture 5. In lecture 5 we will discuss electrostatic of conductors. At first we have to discuss what conductor is. Okay, so we have to discuss about conductors. We know that generally metals, the outermost electron is 1, 2 and 3 numbers. Okay, so we can draw a diagram. Let us consider copper, generally used in electrostatic. So we know that the atomic number of copper is 29. Therefore its electronic configuration is 2, 8, 18 and 1. That is what in the outermost electron number of, that is in the outermost shell, number of electron is 1. So if this is what, nucleus, then we can consider this is what, first shell, this is second shell, third shell. There are 8 numbers of electron, like that. 8 numbers of electrons are there. Okay, there are 18 numbers of electrons, and in the last shell the number of electron is how much? 1. Okay, only 1 electron in the outermost shell. Now if we apply energy to this electron, then it will remove easily. Okay, basically in conductors, in normal temperature or in room temperature, that is energy is there. If in that much of energy, this electron is what, removed from this shell and move here and there in the conductors. Let us consider this is a copper wire, that is conductor. Okay, there are lots of atoms are there, those are copper atoms. Okay, if those are copper atoms, then every copper atom have 1 electron in its outermost shell. Then the electrons from each atom can eject. Then these electrons are called, then this electron is ejected and moving inside the or interior the conductor. What is its direction? Random. It will move here and there with many directions and collide each other. Okay, therefore those electrons are called free electrons. Okay, these electrons which are free are responsible for current. Okay, these free electrons are responsible for current, and those electrons which are in the shells, innermost shells, those electrons are called valence electron. Valence electron, and this is what, free electron. Clear? Okay, now if we apply electric field to the conductor, then electron will move from one position to another position. That is, it will acquire velocity. Okay, this is called what? Conductor. If we apply external electric field, then the electron will acquire velocity. This is called, if we apply external electric field on the conductor, then the electron will acquire velocity, not electron. Electrons will acquire velocity. Clear? Okay. these are called free electrons, or these are called valence electron, bound electron, which will be bounded in the cells, because these electron, here the 18 electrons are there, these electrons we will be not able to eject it out. Okay, it will be possible, then it will require very high energy is required to remove this electron from this inter cells. Clear? These are conductor. Now we are moving to non-conductor. What is non-conductor? Okay, non-conductor. We know that generally non-metals have 7, 6, 5, 4 or 5, 4, not 4. Generally, these are the number of electrons in the outermost shell of the atom. That is why we will be not able to move this number of electrons from the outermost shell. Okay, because it requires very large energy. Clear? If this requires very much energy, that is in that case, in the small or the general electric field, we will be not able to move this number of electrons or electrons from the outermost shell. Okay, that is why there will be unavailability of what? Free electrons. There will be no free electrons. If there is no free electrons, then we will be not able to have current. Clear? That is why if we apply external electric field, on the non-conductor, then there will be no velocity of the, there will be no what? Free electron. There will be no free electrons in non-conductor. If there is no free electrons, then there will be no scope of velocity. Clear? These are metals and these are conductors and non-conductors, and about the free electrons and bound electrons. Clear? Next we are moving to the properties. That is, inside a conductor, electric field is 0. Okay? Inside a conductor, electric field is 0, number 1. Okay, let us consider this is a conductor, this is what? Conductor. Okay, we apply an electric field here. Let us consider those are plus charges are there and minus charges are there. Okay, therefore there will be an external what? External electric field. Okay, there will be an external electric field of intensity E0. Let us consider E0 is the intensity of external electric field. Now, when external electric field is applied or a conductor is placed in an external electric field or having intensity E naught, then the electrons, free electrons present in the conductor will move towards minus side. Okay, move towards what? Minus side. And the positive ions are repelled by these positive sides and attracted by these negative sides. Therefore, the positive will be in this direction. Positive ions will be in this direction. Clear? Those are the positive charges present inside the conductor, and those are the electrons present in the nearby positive charges. Clear? Then what will happen? There will produce an electric field called induced electric field, that is in the direction from plus to minus. Plus to minus. Okay? This is the direction of what? Induced electric field in the conductor. Okay? The induced electric field, let us say E induced, is increased until it is equal to the applied external electric field E naught. Clear? That is what? When E naught is equal to E induced, then there will be no movement of electrons. Okay? Therefore, the total electric field inside the conductor is, let us consider, we can write the total electric field inside the conductor E is applied electric field plus induced electric field. Induced electric field. This is the total electric field E. What is the applied electric field? That is E naught plus induced electric field. See, induced, this is E induced, okay? E induced, this is the electric field, but you can see that the direction of E naught is from plus to minus, that is in this direction, and produced induced electric field is from positive to negative, that is the opposite from this E naught. Then we can write, oh sorry, this is E induced. Okay, again at equilibrium or at the last stage, what will happen? E induced is equal to E naught, since E naught is equal to E induced. Okay, therefore E is equal to E naught minus E naught, that is 0. Clear? That is what? Inside a conductor, electric field is 0. Number two, there is a point in the book, at the surface of the search conductor, the surface of a searched conductor, electrostatic field must be normal to the surface at every point. Must be normal to the surface at every point. Okay, this is the heading. At the surface of a search conductor, electrostatic field must be normal to the surface at every point. Okay, let us consider this is a conductor. We already knew that inside the conductor electric field is 0. Okay, inside the conductor electric field is 0. Therefore, now, okay, now at the surface of the charged conductor means, let us consider this is positively charged conductor. Okay, fine. Let us consider this is the direction of electric field. Okay, this is the direction of electric field. If this is the direction of electric field, then let us consider this is angle theta. That is, theta is the angle between the surface of the conductor and the electric field. Then we can resolve this electric field into two parts, that is E sin theta and E cos theta. Okay, E cos theta. Clear? If this E cos theta component present, then what will happen? This charge, or this charge, any charge can be moved from any point, from this point to this point, any point, because E cos theta is what? Electric field, component of electric field. This electric field can affect these charges and can move from one point to another point. That is not possible because we are studying what? Electrostatics. Clear? Charge should be at rest. Clear? Since these charges should not be moved from one point to another point, that is what E cos theta should be equal to 0. Clear? If E cos theta is 0, then what? Theta should be what? Theta should be 90 degree. Okay? If theta is 90 degree, then what? Then at the surface of the charged conductor, electrostatic field, that is E, must be normal. What is that? Theta should be 90 degree to the surface. At every point. At every point, you can consider, at any point, you can consider theta is 90 degree. Clear? In this case, if there are positive charge, this is the direction of E. Okay, this is the direction of E. This is what? At the surface of the charged conductor, electrostatic field is normal to the surface at any point or at every point. Clear? Fine. This is the second one. The third one is clear. The third one is in the interior of a conductor can have no axis charge in the static situation. Okay, clear? Okay, this is what, let us consider this is a conductor. Okay, in the interior of a conductor, we can assume there are lots of plus minus charges are there. Okay, some ions are there, some electrons are there. Okay, in the static situation we are considering, okay, these are lots of minus are there. Let us consider this is a small volume element. Okay, if this is a small volume element, we can see, if we see the flux phi, okay, if we see the flux phi is always 0 here. That is what? That is, there is no axis charge. There is no axis charge. Okay, let us consider there is some positively charged ion, that is charged conductor. If this is charged conductor, then the charge should be on the surface of the conductor, because the since interior of the conductor, inside the conductor, electric field is what? Electric field is 0. If electric field is 0, that is what? There is no excess charge. That is plus and minus ions are neutral. Okay, if neutral, and we consider what? A small volume element V. Then through the surfaces of this volume, that is surface of this volume, there is no flux passing through. Therefore, we can say the total charge Q is equal to 0. That is, there is no excess charge inside the conductor or interior the conductor. Okay, next one. Number 4, electrostatic potential. Electrostatic potential is constant throughout the volume of the conductor and has the same value as inside on its surface. What is this? Here, electrostatic potential is constant. What? Electrostatic potential is constant throughout the volume of the conductor and has the same value as inside on its surface. Okay, let us consider this is a conductor. Clear? This is what? Conductor. And let us consider there are some positive charges. Okay, this is what? Some positive charges. And inside the conductor, electric field is what? 0. If electric field is 0, then we also can found then this is what? Electric field, which is perpendicular the what? Perpendicular to the surface. And there is a component what? E cos of theta. Clear? Theta is what? Theta is what? 90 degree. If theta is 90 degree, that is E is equal to what? 0. We found that on the surface, electric field is 0, and inside the conductor is also electric field is 0. Clear? Since electric field is 0, we can find, and already we know that the relationship between the potential and electric field is what? E is equal to what? Negative potential. E is the negative gradient of potential. In this case, here electric field E is equal to 0. That is what? Minus dV by dr is equal to 0. Clear? That is what? dV by dr is equal to 0. We know that derivative of some constant is equal to 0. C is what? Constant. Here what? Phi is constant. Here Phi is constant. Clear? V is constant means what? Inside the conductor, and on the surface of the conductor, the potential is constant. Here, electrostatic potential is constant throughout the volume of the conductor. Inside that, we know that the interior of the conductor electric field is 0. That is what? Interior of the conductor potential is what? Constant. And on the surface of the conductor is also electric field is 0 and potential is also what? Constant. Clear? This point is clear and has the same value. We know that V is same all over the surface of the conductor and inside the conductor. Clear? It is electrostatic shielding. Okay, what is the meaning of shielding? Shielding is to protect something. Okay, shield. Electrostatic shielding is we have to protect some region from electric field. Clear? We already know that electric field inside a conductor is what? Electric field inside a conductor is what? Is 0. That is what? E is equal to what? 0. If electric field is 0, then we can consider this is a cavity. This is what? A cavity. Clear? This cavity means the cover of this cavity is what? Metal. If there are some charges present, that is there what? Electric field is there. If there is electric field, then we know that inside the electric field, inside this cavity, electric field is what? 0. Clear? What does it mean? It means inside the cavity, there is a region of the cavity is free from electric field. Okay, this can be applied to some electronic equipment which is very sensitive to electric field. That is, we can protect some electronic equipment from electric field. Then what? Let us consider this is electric equipment. This is electric equipment, and we cover it with some what? Metal body. If this is covered with metal body, okay, if this is covered with metal body, then what will happen? Then if some electric field is trying to affect the electric equipment, then this metal body will behave as cavity and it will protect the equipment, and electric field will be 0 inside the metal body. That is what this phenomena is therefore called electrostatic shielding. Okay, so we can write electrostatic shielding is a process by which some by which we can make electric field free region. Okay, electrostatic is a process by which we can make electric field free region. Okay, we can give there is an example. If you are traveling inside a car and thunderstorm comes in, and thunderstorm are on the all over the car, then what will happen? We know that thunderstorm creates very large electric field. Okay, if that high electric field is on the car, since on the car, then what will happen? Car is what? Covered with metallic body. Clear? Okay, since it is covered with metallic body, if electric field is on the that metallic body, that is what? Inside the car, the region will be what? Electric field free. That is what? Thunderstorm cannot affect a person inside a car. Clear? On the other hand, if you are moving or traveling on the bike, then what will happen? The electric field can what? Destroy you. Clear? This is what? Electrostatic shielding. Thank you.